Number 10, I'm going to do a series of problems. I think my goal is 10, 12, 14, and parts of 17. And I'll see, I don't want to make each video too long, but number 10 has its unique little features. For instance, it's giving you f prime and then asking you some questions about it, which actually is itself kind of interesting. So you have to understand it's a conceptual question about, all right, what does a derivative do for me? So you think of f prime of x as just, that's the given function. It says, on what intervals does f prime of x increase or decrease? So you have to kind of like embrace the f prime idea and just say, okay, if I want to know about something that increases and decreases, I want to know when the derivative is positive or negative. And so one way you can kind of think about this is if you could actually just delete that whole f prime note and just call it something else, called like h of x. All right. Now, in my mind, I'm thinking, all right, h of x, you're just actually f prime of x. But I took you out so that I could answer these questions in a way that I kind of understand. So what I'm going to do is say, all right, h of x, if I want to know when you are increasing and decreasing interval-wise, then I think I need the first derivative. So h prime of x, which is about slopes, which means increasing and decreasing kind of ideas. Then it's 2x plus 5 is the derivative. It increases and decreases around what we call a critical value. So when you set a derivative equal to 0, what you're going to get is either a bottom of a valley or a top of a peak. And around that, you'll notice there's a change point in there. It's uphill on one side and downhill on the other side of those little pink dots I put in there. And so that's why we like to know when the derivative is equal to 0. Remember, that's the horizontal tangent location. We're actually establishing that. So I'm just going to set it equal to 0, subtract 5, 2x equals negative 5, and then x equals negative 5 halves. That means that's the point. It's either a peak or a valley. On either side, it's either increasing or decreasing. So you can graph it and tell me. Now, I happen to know something about this graph. If you go and look at it, this is a parabola. So I know what it looks like. It faces up like this. So wherever negative 5 halves is, it's at the bottom of a valley. So I know on the left-hand side, it is decreasing. It's downhill from all the way up to that negative 5 halves. So the way we write it is an x interval notation. From negative infinity up until negative 5 halves, those are x values. That graph is going downhill. And then around that, on the other side of that critical value, negative 5 halves to infinity, it's going, well, I wrote them in the wrong spots. Well, here, I got an idea. I'll just switch my words around. I don't want to switch the other part. There we go. I was saying the right things and I put them in the wrong spot. You notice on the left it's going downhill, and on the right, let's put a cool color on there. Let's say it's going uphill in green or something. That's a positive uphill motion on the right-hand side of that graph. So now I'll label it correctly. So on the left, it's downhill, decreasing. On the right, it's uphill, increasing. So those are the intervals that we plug in. The thing is, remember, it's asking about f prime. Well, I renamed it h of x so that I could kind of have a sense of that. So you go negative infinity, and you'd use that symbol infinity up to negative 5 halves. You can use 2.5 if you want, but 5 halves goes in really nicely, etc. And you're done decreasing on the, negative 5 halves to infinity. So that's how that goes, comma, and infinity under symbols, done. To finish this out, then it says, all right, for what intervals is the graph of f? Oh no, find the intervals on which the graph of f is concave up or concave down. Now this one's, again, it's playing with our understanding of what these come from. If I want to know when f is concave up or concave down, what we know about concavity is that it's about the second derivative of whatever we're asking concavity about. So if I want to know about f's concavity, I'm going to need f double prime. What do I actually have in my possession? I have f prime, the equation for it, in my possession. So here's how I'm going to set this up. I am being asked a question about f, its concavity. All right, let's figure that out. And what I need to know for concavity, f's concavity requires f double prime, and we want to know about when it's equal to 0 or undefined. Those are that's the breakpoint. And around those places where it's 0 undefined, I get concave up or concave down. What I have in my possession is the equation for f prime, x squared plus 5x plus or minus 24. So I need to take the derivative one more time of what I've given to get f double prime. It'll tell me a story about f, even though I don't have f anywhere in this. But let's go get f double prime. It happens to be 2x plus 5. I already found that, remember when I did the derivative of h? Now this, if I set it equal to 0, we already know this, right? Negative 5 halves is what we got. Well, we were doing it in terms of x. It said something about increase and decrease. Well, right now, what I want to know is, since I know negative 5 halves equals x, what that tells me is in and around negative 5 halves, my concavity changes in this function f that I do not know anything about. So here's negative 5 halves. On one side of it, it's concave up, one side of it's concave down. And the only way I'm going to find that out, since I don't actually have f in front of me to look at, usually I have the graph and it's pretty easy to tell, I have to do a test of numbers. So f double prime, put in something to the left of 5 halves, 0 would, not 0, I'm sorry, I'm doing the right hand side. To the left of negative 5 halves would be like, I don't know, negative 3 or something. And then on the other side, sorry, I was put f double prime, if I put 0 in there, that'd be a really nice one. And all I need to know is if I plug those numbers in, and it's right here, the equation's pretty simple. 2x plus 5 is what I'm putting it into. Negative 3 into that function, if I put negative 3 in for x right here, 2 times negative 3 is negative 6 plus 5. That is still negative 1. So, and that is negative overall. That means this is concave down on that left-hand side. So concave down. And the cool thing about polynomials when you're looking at them, we kind of already know the right-hand side is going to be concave up, but it's going to be worth testing. Put in 0 in the pink part up there. 2 times 0 is 0 plus 5 is 5, and that's positive. And what that means, it's concave up when f double prime is positive. So we've got this thing now. So it says find the intervals from concave up and concave down. It's concave up forever up until, so concave up, sorry, it's from negative 5 halves to infinity, negative 5 over 2, comma, and then we'll use the infinity symbol. Okay, that's the concave up piece I was just looking at, so we'll go highlight it over here in our little graph. This is concave up, and it's after, to the right of negative 5 halves, so the negative 5 halves to infinity. And then it was concave down on the other side of it. So it's concave down over here, which is negative infinity to negative 5 halves as an interval. So I'll finish this off from negative infinity to negative 5 halves. Got it. That's the interval that we write in there. Then finally it says, find the x values of the relative extrema of f. So if I have f and I want to know anything about its extrema, this is what I know. F has mins or maxes whenever f prime is equal to 0 or undefined, potentially, but we have a polynomial, so that's not going to happen. So it's just when f prime is equal to 0. So if I want to know about f and its relative extrema, maxes and mins, that's what I want to know about. Then I need f prime equal to 0. So do I happen to have f prime? Sure, it's what I've been given all along. So I take the equation that they gave me in the beginning over here, which was x squared plus 5x, like this, minus 24, which is my f prime. That is the one I said equal to 0. It's quadratic. I don't know if it factors 8 and 3. I think might do the trick, so I'm going to factor it because I can't. And if you want to use quadratic formulas, fine. But it looks like x plus 8 and x minus 3, 3 and 5. Sorry, I said 8 and wrote 5. 3 and 8, x plus 8, 3 times 8 is 24, and negative 3 and 8 are negative 24. Yeah, they add to 5. Boom, I got it. That's my factoring. That means what x's make this equal to 0. So negative 8. Negative 8, if I put it in there, I'd get 0 times 0 times anything is 0. If I have x equals 3, and plug it in that function, then I get 0 times anything 0. So those are my two, what I'd say are those are two values. Those are critical values. They're not telling me a relative max or min specifically until either I graph it or I take and test values. And so it's a mandatory kind of put -8, put 3 in here, and what we'll do is we'll test f prime. If it's positive and negative around that critical value, we know this is a peak or a valley at -8. We know it's a peak or a valley at 3. We just don't know which kind. So to go to the left of -8, I'm going to put in -10, for instance. I'll test that. And between -8 and 3, I'll put in 0. It's always a good one to test. And then outside of 3, I'll probably just do 4 and see what I get out of those. Ooh, can't write that number. There's 4. Okay, I'm putting those into the first derivative to see what kind of uphill, downhill action I'm going to see in this thing. Okay, so if I put -10 in to my f prime of x up top here, I'm going to do this mentally. -10 in for x squared is 100, plus 5 times -10 would be -50. And 100 take away 50, and then take away 24 more is still positive. Okay, I'm doing this a little bit mentally. Put 0 in there. Okay, so we're going to put 0 in. I'll use pink this time to kind of highlight where I'm at. Okay, so here comes pink. Put 0 and you get 0. 0 here, you get -24. Okay, that's a negative. Bingo. And when you put in 4, let's use one more color here. We'll go yellow this time. So when I put 4 in here, I get squared at 16. Plus 5 times 4 is 20. That's, positive 34. Oh, minus 24. We're still positive. So seeing that tells me that my graph around either a peak or a valley, it's going uphill, and then it's going downhill, and then it's going uphill. And if that's the case, uphill to downhill means in between there, we got a peak going on. Let me get a different color going on here. Pink. This would be a peak in pink because it's going uphill to downhill. And that means downhill to uphill, that's a valley taking in there. We also know that as a maximum, relative maximum, and this is a relative minimum for the valley. Those are the points we want to put in here, and they're coordinate points. So you want to put, and there's no parentheses given, so you got to go in here. All right. Actually, no, I'm sorry, it says x equals. The maximum is at -8, bingo, and the minimum is at 3. And one more for number 10. It's a long one. It says find the x values of the points of inflection of f. So conceptually, again, if I have f and I want to know inflection points, IPs, that's from f double prime being equal to 0 or undefined. So what I'd have to do is either have f and take the derivative. We don't have f. We have f prime. Oops, I keep writing funny things in there. I have f prime. Okay, so I'm going to give you a little graphic that I've been using kind of consistently. If I want the inflection points of f, what I'd have to get is the second derivative and set it equal to 0 to make that happen. Well, what I have is f prime, as I've had all along, and I take and use that, x squared plus 5x minus 24, take a derivative again to get f double prime, set it equal to 0, which we've done actually several times, and you get x equals -5/2. That's our inflection point that takes place in that particular graph. And we happen to know that it does go from increasing to decreasing around x. We've tested that before kind of passively. So our inflection point is -5/2. There's a lot of things to ponder over this, and I think the help that it offers gives you some more ideas of where this all comes from. But that's the solution to the very long number 10.